Hi, I'm Steve Croft. It's nice to be here with Lyman Page, the winner of the 2018 Breakthrough Prize in Physics. I understand that you had an unusual beginning to your career, and I wondered if you could tell us about what you did between graduating and your first research job.
Okay. So I graduated from college, and at the time, I was thinking about going to graduate school, but it just wasn't a good match. And I saw this advertisement on the bulletin board for research in the Antarctic. So I applied, and I got it. This was with the Bartol Research Foundation, and I went to the Antarctic and spent 15 months there. Saved up a bunch of money from being on the ice and not working, and came back, took the money, bought an old sailboat and up in Maine and rebuilt her, and then spent the next 2.5 years sailing down the East Coast and around the Caribbean. I should say sailing and working on the boat. It's an old boat. It was always falling apart, so we're always fixing it. It's a perpetual state of fixing. And then finally I reached the point, I was with my friend, we were sailing to Panama, we wanted to get to the South Pacific. And we lost the rudder for the second time and broke one of the sails. And I remember the night, and we just said, it's time to go to grad school. I loved physics the whole time, and I'd stayed up with it. I was even doing problems, while sailing. And so we sailed into Jamaica and worked our way back to the Caymans and Belize and Florida, and sailed into Boston. And
Straight into grad school.
Oh well, no. I got off the boat, saw some friends, and went knocking on doors. And I went to MIT, and the office was closed. The graduate office was closed. I went in there to get an application, and completely naive, right, about how any of this stuff worked. And it was closed, and the guy behind me, Herb Bridge, said, "What are you doing?" I gave him a brief spiel about what I'd been doing. And he said, "Do you have a CV?" No. He said, "Well, come by, Monday, and my secretary will type one up for you." And I was so embarrassed, I typed one up myself. And he gave me a bunch of people to talk with. And one of them was Ray Weiss, last year's winner of the Breakthrough Prize. And I just walked in his lab, and I said, "Can you hire me? I need a job. I want to go to grad school, blah, blah, blah." And he said, and I'll condense this a bit, "No, but you can work in my lab." So I was just I worked as a carpenter in Boston and worked in evenings and on the weekend in the lab. And he got me into grad school and started me on this project, and I've been working on the microwave background ever since.
So it seems like taking things apart and putting them back together is a passion of yours?
Yeah. No, I'm an experimentalist, right? I love building things and thinking about how to build them, and spend just as much time in analyzing the data from them. Just to see what the measurement reveals.
So when you were on the boat, did you spend a lot of time looking up at the stars, and were there questions that were sort of gripping you when you were out there?
Yeah, mostly for navigation, trying to figure out where we were. And it wasn't quite, is there the microwave background out there? I sort of knew about it. Mostly, I think one of the books I remember doing while sailing in that particular passage was, thermodynamics, Zemansky's thermodynamics book. So I was more trying to keep the boat going and afloat, and then just sort of, doing something more intellectual and just reading and doing problems. It was a little bit more like that. But, it's absolutely beautiful being out on the ocean. But observing from Chile, the skies from, say, Chile, is much nicer.
So what is WMAP, and how did you get involved?
So WMAP, the Wilkinson Microwave Anisotropy Probe, named after Dave Wilkinson, is a satellite. And the thing we did is we measured this radiation left over from the Big Bang over the whole sky with accuracy and precision and really good controlled systematic errors. So how did I get involved? Specifically, I was walking by Dave Wilkinson's office, and he said, "Lyman, you ought to work on a satellite project." And this was before we teamed up with Goddard, Chuck Bennett and crew at Goddard, NASA Goddard, and so we started thinking about it. Dave and I wrote a proposal early on to develop some of the technology for it, and with in mind this an eventual satellite. And that was funded, and worked on that with Norm Jurasic, a co-winner. We've been working since I started at Princeton, and it just developed, and we had a bunch of different avenues. We talked to a bunch of different people, and then finally our group got together with the group at Goddard, and we just had a great meeting, and it took off, and that's really when the map, they had been thinking about the same sorts of things. That's really when the project took off, and worked like hell, loved it. It took over our lives, I think all of ours. We knew we had this great opportunity, and it worked out, I guess.
And do you find it sounds like your journey on your boat, there was a lot of kind of opportunity to tinker with things as things were going, and that's pretty different to kind of the one-off shot of launching something into space. Was that a nervous experience to kind of strap what you built onto a rocket?
Yeah. No, I remember, when you started out and hearing about these Delta launchers saying, they're 95%, they have a 95% success rate, and thinking, no problem, 95%, that's fantastic, we're there, let's just do it. And then after a few years, and you're getting closer and closer to launch, right? Then it's, what do you mean there's a 5% failure rate? That's outrageous. But anyway, it worked. Everything worked, and those guys did a great job, and because it was great. But going back to the boat, that training, and I didn't realize this until probably halfway through graduate school. It wasn't exactly what I learned, because I got money from being a carpenter and a rigger and that sort of thing. But I think it was just probably the discipline of making something really, really work. Right?
That your life depends on.
It had to work, right? And foreseeing problems if something didn't work, and just planning, and under the as a carpenter, so I'd have to at the end, and so I'd have to get my tools, row out to a boat, make a measurement, come back, build it, put it in, and have it fit.
Do you have young people working in your lab who've had similar sort of hands-on experience, or do they have more conventional routes into science?
A little more conventional, but I'm completely open to but yeah, they're all great. but yeah.
So tell us a little bit about what WMAP discovered and what the implications are for you.
So the thing that we did, and we because we've been making these measurements for a long time. We all had a background in making these measurements, and what we knew is if we could make an all-sky measurement of this radiation that was really accurate, that we could just figure out the parameters that govern the universe. If when we started, we didn't know what they were. We didn't really know what the skies would be like. We had a feeling. We didn't know what the model was, and we didn't know if you really pushed it to the limits, right down to the fundamental limits set by detectors, whether it would hold, like with no hair, right? No garbage in there. Just it's not like, oh, it looks like this. It's just like, no, to the fundamental limits of measurements, does this model hold? And so we designed a system that could do that. And a key piece of that is making sure that fundamental limit is really small, so you can really probe deeply. But that's what we did, and we made the measurement, and we made it so we could extract the cosmic, the cosmic microwave background, right? That radiation from galactic emission and things like that to a really high level, and then what came out of it was this standard model of cosmology, and not just you often hear about we often hear, maybe you don't know, the 6 parameters that govern the universe, and there will be more, but as big a part of that were the processes that led to it, and how we characterize the model, and its attributes, its Gaussianity, its adiabaticity, is general relativity, the right model, all those elements, and they all come together, and that they could all come together was what we were able to do, show that they actually did in a very simple model. And then, after us, and I should say, this is in a very active field with colleagues and competitors, and we're all trying to make better and better measurements. But this was just in terms of control systematic errors and certainty, it was just a whole different thing. And then you see this Planck satellite, a wonderful achievement. They ended up at pretty much the same model, right? Which is just amazing, right? That our universe can be so simply described, and even more than Planck, it's measurements of all these galaxy surveys. It doesn't matter how you look at the universe. It's whether it's supernova or surveys. This is the model. It's a amazing state.
So it's been said that, and your work was a major part of this, that we've entered the era of precision cosmology. Right. Is there anything left to do in cosmology?
Oh, there's tons. We've just begun. Yes. No, I think, we're all involved in projects now. For example, let me just name like 3 things. One is, it's pretty clear that we're going to be able to determine the sum of the neutrino masses, which is, this is in the realm of particle physics. And we don't do it the same way, right? We just measure their density. So we're a blunt probe, but a powerful probe. And we're going to do this because they're going to be the 7th element in the model. Because right now they contribute less than 1% of the density of the universe, and the models are good to sort of the percent level, but as we improve them with these current measurements, we'll get down so that 1% rises and is clearly visible. And that's happening now. So that's really cool. We can search for if there are new particles that haven't been measured on Earth in the early universe. There might be gravitational waves left over from the Big Bang, which would be really, really cool. Right? So that would be this connection between gravity and the quantum regime as a start, and a key observation that would help identify the right model, the best model of the early universe. So that's fun. There are. Let me stop there. There are just so many. There's just so many things to do. It's just it is now. There are optical telescopes all over the world. We're used to it. There will be more and more CMB telescopes because it's just such a powerful observable. It's like you have this flashlight at the edge of the observable universe that's so clean and so well characterized, and you can look between us and it, and you can, since we know this so well, you can look for tiny perturbations in it and figure out what's going on throughout the volume of the universe, and that will just keep going. It'll be ever more important. So,
great.
Yeah.